Hello, welcome to this session where we look at the derivation of Heron's formula, which is used to determine the area of any triangle provided we are given the length of the three sides. My name is Norman Inyang, and we base our derivation on Pythagoras' theorem. So if you're given a triangle which has three sides, ABC, which are of course accompanied by the points ABC. So if a perpendicular bisector is dropped from the point B onto the line AC, you can see that we are able to come up with two right angle triangles there. The first of those is a triangle ABD, the smaller one, and we also have the triangle CBD, of course sharing a height of H, and they have different bases, all derived from the length B. The smaller of those is the length X, and the other is B minus X. So we are going to use Pythagoras' theorem to determine the relationship between the three sides. First establish using X, and then we can eliminate X to come up with a relationship with ABC, and eventually substitute it in the formula of area. So let's go ahead. So from elementary school, area of a triangle is always and shall be given by a half times base times height. So that can be our basis for equation 1. So using Pythagoras' theorem, we can use triangle, look at the relationship between the two triangles. First, using X. So for the first triangle there, the X squared plus H squared is equal to C squared, and making X squared the subject, you have X squared there as C squared minus H squared. We can also make X the subject, and X shall be the square root of C squared minus H squared. So that can be our basis for equation 2. So on to the next triangle CBD, we have B minus X squared plus H squared being equal to A squared. So we can square that, and our B squared minus 2BX will be equal to that. So substituting to eliminate X there in that equation, remember we had got the expression for X squared in equation 2, so and for X, so substituting there B squared minus 2BX, putting there X squared, which was root of C squared minus H squared, now that was X, and then X squared was C squared minus H squared there. So if we make that successful substitution, we shall come up with that expression, and we can proceed further to simplify the expression. So B squared, we are simplifying, of course, taking C squared minus H squared to the right hand side, and we are able to come up with that relationship with the square root on the right hand side. So by squaring both sides, we now have C squared minus H squared being equal to B squared plus C squared, being equal to that expression there over 4B squared. So continuing further, making H squared the subject there, we are able to come up with that expression. We are able to come up with that expression there, and that is our expression for H squared. That can be our equation 4. Now, one of the most important parts of this derivation is coming up with this relationship, being able to eliminate the products, and then come up with a single relationship between the three parameters A, B, and C. So as you can see here, we have an expression here. This is a 2BC all squared, and also we have B squared plus C squared minus A squared all squared. So there is a relationship which we can exploit from the difference of two squares. So if we have two squares, we can surely establish a much less complex relationship between these variables. Let's move on. So from the difference of two squares, x squared minus y squared is equal to x minus y into x plus y. So one of these functions, preferably 2bc, can be looked at as our x squared. 2bc can be looked at as our x squared, and then x plus y can be 2bc can be looked at as our x, and this whole expression can be looked at as our y. So if that is true, then we can establish that relationship, which I am going to explain shortly in our simplified expression there. I will be able to explain that. So this is the first function. So using difference of two squares, so this is our x and all this is our y. So x plus y is simply this plus that, and x minus y is this minus that. So putting these terms together, 2bc and a squared, you can see this is an expression for b plus c squared, and this one would also be an expression for b minus c squared, except the negative one. So we put out the negative one outside here, and now you can see that this expression can translate into b squared into b plus c squared there. So once we have done that, we can do the simplification. You can see this is b plus c squared minus a squared, and this is negative 1 into b minus c squared minus a squared. So we can put the negative back inside, and we have a very, very, very simplified relationship there. Again, our difference of two squares will also be used to simplify that expression, and once that is done, again, this is our x and this is our y. So x, simplifying that further, will now result into the relationship below there. So you can see that we have managed to simplify this expression using the difference of two squares. So having got, let me just go back and shed some light there in the previous expression. Remember, our expression resulted into this relationship. So if we use difference of two, if we use difference of two squares, then we are surely going to be able to come up with a summation as we got in that expression. So exploiting the relationship further, we shall now have b plus c. This is our x and this is our y, and this is also our x and this is our y. So you can see that we shall be able to come up with a very simple summation of b plus c plus a into b plus c minus a, and this one also we shall have a plus b minus c, and then we shall also have a minus b minus c, and where this is the simplified expression. This is the simplified expression. So using perimeter of a triangle, which is a plus b plus c, let that be equal to our p. So if that is true, then we have the following relationship: b plus c minus 2a is now equal to p minus 2a, because of course if we introduce here a plus b plus c, then we have to subtract 2a, so that this a minus 2a results in negative a, and everything else is the same. So for the three sides, that shall be the relationship. So having got this relationship, we are now able to substitute in the expression of 2bc squared plus a into this expression, and if we do that, you can see that this was this now long expression now only becomes P into P minus 2A, P minus 2B, P minus 2C. That's rather simplified. So if we substitute equation 4 in equation 5, and of course eventually we take the square root, we have this relationship as the expression for h squared. Now taking the square root, we shall have h as being equal to 1 over b, this expression. So if we substitute in equation 1 of area is equal to a half times base times height, we substituting this h, and of course our base was b, so we come up with this expression. Now of course the two b's cancel, and we can attempt to put the square root into the bracket. So if we are to put the square root into the bracket, we also know that a half is equal to root of 1 over 4. So it is 1 over 4 that will go into the square root sign. And so we are able to have 1 over 16 into the expression. But also note that 1 over 2 to the power 4 is equal to 1 over 16. So we can split a half into each of these 1, 2, 3, 4 functions. And we are able to come up with P over 2, P minus 2A over 2, which again we can subdivide into the individual functions. So you can see that we are moving closer to Heron's formula. We have P over 2 minus A, and that. So if S is equal to P over 2, we can replace in the equation. That's area of a triangle shall be equal to, you can see the famous expression for Heron's formula coming in there in our derivation. So it's a simple derivation. We use the simple formula of area is a half times base times height. Then we use a scalene triangle. We drop a perpendicular bisector, create two right angle triangles, use Pythagoras theorem, exploit the relationship of the difference of two squares, and substitute back into the expression for area of a triangle, and there is the derivation. So if you like this video, you can subscribe to our YouTube channel. Alternatively, in the comments you can make suggestions about any important mathematical videos you want us to look at. Thank you.